I'm going to need a bigger workbench.
Welcome to the RC Adventure channel, everybody. This is part 5 of the airplane scratch building series. Going to be covering two things in this video. First, it'll be servo selection and the design of the mechanical control linkages from the servos out to the flight controls. Then after that, I'm going to show you a little bit about how the wing's built. Now, first for the servos. There's this school of thought that when you're selecting the servos, you simply look at the size of the airplane and go, oh, okay, well, that's a 50, 60, 70-inch wingspan, so I'm going to use a standard servo. Or it's a 30, 40-inch wingspan, I need a micro servo or something. Well, that rule of thumb does generally work. You don't really know for sure if you're going to be putting enough power out to the flight controls to make them move the way you need them to in all possible situations. Here's the way I like to do it. First, I figure out the torque that's required to move the control surface to its max deflection at the highest possible airspeed. For those of you that went hop skippity jumping down the hallway in high school going, yay, I get to go to advanced calculus, here's the formula for you to follow. All of us normal people, on the other hand, are going to want to go to this website. It's got a bunch of great calculators on it to figure out different things, including how much torque is needed to move your flight controls. For the example, I'm going to use my 40 size J3 Cub just because I know how fast it can go. Has a wingspan of 78 inches, weighs about 7.5 pounds, and it tops out at a whopping 60, 65 miles an hour, full throttle in a dive. So for speed, I'm going to put 100 kilometers per hour. That's 63 miles an hour, give or take. Then I'll put in the aileron cord, and the combined length of both ailerons, because they're both going to be powered off the same servo, I'm going to set the servo deflection and the control surface deflection to the same number. That way I can see how much torque is going to be required at the control surface. Then after you hit calculate, you'll see that it's going to require 57.5 ounce-inches of torque to move the surfaces in the scenario that we've set up here. This isn't the end of the story though. I'm going to be doing scale flying with this airplane, not 3D aerobatics, so I don't need twitchy, fast-moving control surfaces. And what that means is I can change the linkages around to work kind of like a gear reduction. In this case, going for 2-to-1, so it doubles the servo's torque. And now I only need 19.1 ounce-inches of torque at the servo to move both ailerons to their max deflection while at full throttle in a dive, which is rarely, if ever, going to happen. So I probably don't even need to be up near the recommended torque you see over here of 24.8 ounce-inches, but somewhere between 20 and 25 will be fine. Your elevator, on the other hand, you're going to want to make sure that you've got plenty of extra torque available so that you know that you can pull out of that dive if you have to. And just to play around with the numbers for a little bit, when I slow it down to the speed that this Cub normally cruises around at, which is a little over 30 miles an hour or 50 kilometers an hour, now you see it only takes 4.8 ounce-inches of torque to move the ailerons to their full deflection. And with that low of a requirement, a micro servo is fine. And that's actually what this Cub's been flying around with for a little over 4 years now without any problems whatsoever. Now that I know the torque required, I can move on to designing the linkages in CAD. Since the Fowler flaps have the simplest linkage design, I'm going to start there. They're going to be controlled by a single servo in the center of the wing. That servo is going to rotate 180 degrees to move the flaps to their fully deployed 40-degree position. For those of you doing the math, that's going to work out to a 4.5-to-1 mechanical advantage, which won't be needed, but it will reduce load on the servo some, which will reduce current draw on the battery by a tiny bit. Also, you'll notice that when the flaps are in the fully extended and fully retracted position, the push rods and the servo arm are in line with each other, so it's going to take very little power, if any, to keep the flaps in those two positions. Keeping in mind that there's a good chance that you're going to be landing with a dead or nearly dead battery, it'd be kind of nice to keep that current draw to a minimum. The main thing that I needed to figure out here, though, was how long did the servo control horn need to be to move the flaps the necessary 40 degrees. And what I've come up with is that the flap control horn over here is actually moving back 1.6 inches. So the horn needs to be 0.8 inches long. Moving over to the ailerons, you'll see that again they're controlled by a single servo in the middle of the wing, which will be connected to Sullivan goldenrod, which will run all the way out to the bell crank, which is connected to a wire push rod, which is connected to the ailerons. You may have noticed that the servo control horn is kind of funny looking triangular thing. This is going to give me a 50% aileron differential, meaning that the aileron's downward travel is only 50% of its upward travel. The reason for designing aileron differential into an airplane is this. If you remember, there's two different types of drag, parasitic and induced. Induced drag is what you get when the wing generates lift. When an aileron travels down, it increases lift on that wing, and therefore increases induced drag. On the opposite wing, however, the aileron's traveling up, which is decreasing in lift and therefore decreasing induced drag. But the aileron itself actually deflecting is also causing some parasitic drag, so you want it to travel up more to increase the parasitic drag to match the increase in induced drag on the opposite wing, giving you a coordinated turn. Anyway, enough talking about it. Let's build it. First thing I'm going to do is cut out all the ribs. Now you're probably wondering, well, what's an easy way to cut out all 31 of these ribs that's not going to take all day to do it? Well, let me show you. Start with a paper pattern, as I've done with all my other parts. And then I use that as a guide for some fairly rough-sized rectangular pieces. And just cut out a whole bunch of these. In this case, I need 14 of them. Once I got all the pieces rough cut, then I like to put a small dot of medium CA right in the middle of each one and glue the whole stack together like that. And now it's over to the scroll saw. In part 2, I briefly mentioned the spar material. Well, this is it. This is aviation grade spruce. I got it from Aircraft Spruce and Specialty Company. It came in a 8-inch wide by 4 foot long by 1/8-inch thick board, and then I just used a table saw to cut it down to the sizes that I wanted. It's a little bit of extra work, but in the end it's going to equal a much stronger spar than if I just went with the woods available at the hobby shop. Here's what I got for the flap so far. It's 1/16 inch balsa sheet on the bottom and the ribs, and then 1/32 inch balsa sheet for the top. It's got to be able to make the fairly tight curve here. That's why I went with something so thin. And then the leading edge is 1/4 inch square stick. And then the last piece would be the control horn here, which is made out of 1/16 inch plywood. For the flap hinges, I've made them out of 1/16 inch thick heavy ply with a 1/32 inch piece added on either side, and then a 256 bolt nut that goes through to act as the hinge. The triangular piece here is going to be attached to the flap, and then this curved piece will be attached to the wing's rear spar. Next up is to install the hard points in the wings for the pontoons. I've made these out of some spruce scrap that I had sitting around. Now this isn't the same aviation grade spruce that the spars are made from. This is some leftovers from a display stand I made a few years ago for one of my sailboats. Once I cut it to size, I cut a groove through the bottom here and then drilled a hole right there through it. And this will accept the wire that's going to become the leg for the pontoon. Basically, the wire will come up from here, then bend 90 degrees, go through the groove, make another 90-degree bend, and then go through the hole. And then there's going to be 2 nylon straps going across it to hold it on there. Kind of the old school way of attaching landing gear on an airplane. You may have noticed this little nut here on the bottom. Well, that's because this hardpoint also serves as the mounting location for the aileron bell crank. In fact, you'll see that the top is also at an angle, and the reason for that is to put the plane of rotation of the bell crank in line with the push rod that's coming out and going to the aileron. I've also made these 2 1/8-inch thick light ply doublers that are going to sit on either side of the block like so, and they're going to be glued to the ribs and the forward wing spar, and that's going to ensure that any load that's put on this block gets transmitted to the spar and not to the ribs. And there we go. Wings are all framed up, joined together, and barely fitting on the workbench now. The plans call for joining the halves with a strip of fiberglass on the middle here. I've taken the extra step of putting some pieces of carbon fiber on the top and bottom of the spars. I've had this stuff sitting around for 21 years. Figured I'd eventually find a use for it. It finally did, at least for a few pieces anyway. Also, you see in the center section here, I've got these pieces of spruce that are running crosswise. These are going to be the mounts for the servos, which are going to go right here in the middle. You'll see I've got the goldenrod in place, running out to the flaps. And then also out to the aileron bell crank. Up front here, I assembled the nacelle frames by first tack gluing everything in place with CA. The firewall only got a single dot of CA on the top. That way I could use some wedges and my E-flite Angle Pro 2 to adjust the thrust line to 2 degrees positive. Once I was happy with where everything was, I epoxied in strips of fiberglass on all of the joints here, and everything is now super strong and ready for the power system. Here's a couple of quick tips to make life easier when you're working with goldenrod. As you probably know, the surface of the outer layer needs to be roughed up to give the glue something to hold on to when you're securing it in place. So you simply take a power drill and you gently chuck that outer piece in the drill. You take some, I'm using 400 grit paper, something close to that should work. And there you go. In just a matter of seconds, you can rough up the entire length of the outer tube. Goldenrod trick number 2 is an easy way of putting the threaded insert into the push rod. Simply chuck the threaded piece in your drill and start threading it in. Once you get it going, you're going to want to hold it with a pair of pliers, and then you can just run it home just like that. All right, let's get those servos installed. And there we go. I bet you didn't know I was a Q, huh? All you Trekkies know what I'm talking about. And for the rest of you, go watch some Next Generation. You'll figure it out. Anyway, in the back here is the aileron servo, and I made its horn simply by taking one of those large plastic wheel horns and cut it to shape, drilled some holes where I wanted it. Pretty straightforward there. The flap control horn is a lot harder though. I didn't have anything that was quite big enough for it, so I used one of the small plastic horns. And then at first I tried gluing this piece of 1/16 inch heavy ply over the top, but the glue wasn't going to hold, so I drilled and tapped for these small countersunk screws that I had in my collection, and that seems to be good enough. If it doesn't work though, I'll just switch to an aluminum horn and that'll definitely work. But you know, for now I think this will do, so one way to find out. And I cannot tell you how it feels to see this airplane sitting here on the bench, really looking like what I envisioned when I started all this. This is super exciting. I cannot wait for spring to get that first flight in. Already getting nervous for that first flight, but still, Yeah, it's going to be awesome. I'm going to wrap this video up right here though. The next one's going to cover the design and installation of the power system. In the meantime, if you want to see more like this, check out my Facebook page. Also, be sure to check out the description below. There's going to be links to some of the tools you've seen me using here and some of the other products. And if you like this video, be sure to hit the like button. If you want to see more like this, hit that subscribe button. And if you want to know when the next one's up and ready, that's what the bell icon's for. Until next time, remember, the best airplanes are the ones you built yourself.